Hi, I'm Doug. I'm a math teacher. I love physics. And you can imagine that I've read and watched a lot of science fiction. As a child growing up, I would often look up into the stars at night and wonder what's really out there. Now, I really want to find out what space really is. And more importantly, can you stretch it?
Let's punch it.
In this part 1 video, we're going to learn how to describe space. The first leg of our journey starts with the ancient Greeks, the ones that gave us geometry. Pythagoras, one of the ancient Greeks, discovered something about right triangles, the Pythagorean theorem, a squared plus b squared equals c squared. It's a pretty important formula in geometry and in math in general. Let's see why. A big chunk of geometry is right triangles. So we get the Pythagorean theorem and trigonometry from right triangles, and that leads us to circle geometry. Measuring length in the plane, such as the distance between 2 points A and B, would make very good use of this Pythagorean theorem. So a squared plus b squared equals c squared would allow us to find c if we knew a and b. Let's see how this would work out. Okay, so let's talk right triangles and the Pythagorean theorem. A squared plus b squared equals c squared for a triangle that has sides 3 and 4. By plugging in a and b, 3 and 4, we calculate the squares of those numbers 9 and 16 to have a sum of 25, and when we want to solve for what squared is 25, we take the square root of both sides, giving us a side of 5. Since c squared is equal to c times c, or 5 times 5, 25, c squared equals 25, we can now measure length, or distance, in the plane, using the Pythagorean theorem. A few abstract geometric objects include a point, a zero-dimensional object, which means basically that it has no measure. A line or a line segment is something that is a collection of points, so that it makes up a one-dimensional object which is described by the measure we call length, or perhaps distance. A surface, like a plane, which would be a collection of lines, that makes up a two-dimensional object, and that is described by length and width, so this allows us to also define a measure called area. Three-dimensional objects are simply a collection of surfaces. Three-dimensional objects typically have length, width, and height, 3 dimensions, and therefore from that we can calculate something called volume. Now that you have a feel for geometry and a little bit of algebra, we're ready for coordinate geometry. Alright, some coordinate geometry time. So coordinate geometry consists of 2 rulers, an x and y axis. We have points which are ordered pairs, x, y, and equations that can describe graphs on this plane. A little notation. In the Cartesian plane, we have things like the shortest distance between 2 points to a straight line can be defined using coordinates x1, y1, and x2, y2 as the 2 points of the line segment. And we can define vertical and horizontal distances, delta y and delta x as well. In coordinate geometry, we have the distance formula, the midpoint formula, and the slope formula as our heavy hitters, and you'll see the vertical and horizontal distances show up in them. A quick review of coordinate geometry. So you start off with a point or coordinate, which is given by the ordered pair xy. A line, a collection of points, can be formed by relating the variables x and y together through an equation, y equals mx plus b. The line is graphed, or you could say lives, on the coordinate or Cartesian plane. This plane is formed by the x and y axis, and we can graph anything like a line by relating x and y on this plane. In order to understand space in 3 dimensions, we're going to have to dive into vectors. You can think about a surface as an extension of a shape on the xy plane, such as a parabola, the z-axis providing the 3rd dimension. A 3-dimensional coordinate, or ordered triple, x, y, z, can be described using vectors. So a vector v can give you the distance from the origin and the direction that a coordinate point xyz is from the origin, and xyz are called the components of this vector. This vector also has vectors I, j, k, which are called unit vectors, or the basis vectors for this vector representation. So a surface can be described, such as a plane, in 3 dimensions, where we can think about the z-coordinate as the dependent variable and x and y are independent variables. So the equation z equals x plus y can describe this plane, and we can see this if we graph this in GeoGebra. So in green here, you see the plane z equals x plus y. I'll rotate it here for you a little. And this is just one way to represent a function of 2 variables in 3 dimensions. So there are many different ways to describe 3-dimensional space. And in this case, dealing with equations can also connect us to the geometry. So vectors are these mathematical objects that have both magnitude, that's length, and direction. For this reason, we're going to represent vectors with an arrow. You might be familiar with this sort of notation: an initial point and a terminal point. In the coordinate plane, we can represent this on the xy plane with the vector telling us things about the space, and even in 3 dimensions, we can perform a little vector algebra to give us things like volume in 3-dimensional space. We can also use vectors to describe things like fields. The electromagnetic field is one of those examples. When we start working with vectors, we begin to develop vector algebra, and that leads to something called linear algebra and linear transformations. These are all very important in the discovery and the description of space. In fact, I'm going to introduce you to something called a matrix.
Shall we play a game?
Oh.
Let's talk about graphing linear equations for a moment. The equation y equals x plus 1 has a slope of 1 and a y-intercept of 0, 1. Now this equation can also be described by a different equation, although it is the same equation, it looks different. The equation 3x minus 3y equals negative 3 is actually the same equation, just written a little bit differently algebraically. It has the same y-intercept of 0, 1 and the same slope of 1. Now if I were to graph a second equation, 3x plus y equals 9, now we have a system of linear equations, and they have a point of intersection. The point 2, 3 is their point of intersection, and it represents a unique place a unique x and y that they both share, a solution to the system of equations. There's a geometry associated with this system of equations. So let's dig into the algebra a little bit more. If you wanted to graph two linear equations, you typically put them into slope-intercept form, y equals mx plus b. So these two equations written in mx plus b form yield a graph which shows us the intersection point is 2, 3. Now, if we wanted to extend this to, let's say, the algebra part of this, and just use the algebra, not the graph, then we're talking about solving a system of equations. Here we're going to use the method of elimination. Now, using row operations, we can multiply an entire equation by a number to change its form. And in this case, if you notice, we changed the 3x to a negative 3x, and we're able to add these two equations to give us a simpler equation to solve. We get y equals 3, and through some back substitution, we find that x equals 2. Putting this together as a coordinate point, we have the coordinate point 2, 3, the point of intersection of the two graphs. The general form for the equation of a line can be given as ax plus by plus c equals 0, with a, b, and c being real coefficients. If we extend this to a third dimension, with z being that third dimension, the equation of a plane is ax plus by plus cz plus d equals 0. Now, a system of three equations and three unknown variables geometrically represents three planes in three-dimensional space. Now, these planes can intersect each other, so for instance, two planes intersect here through a line. And so if you notice that as I rotate this here, that line is visible, but if we introduced a third plane, then the only place that they intersect would actually be a specific point in three-dimensional space. And so if we solve the system of three equations and three unknowns, we should be able to find this unique point in space, x, y, z. So let's take a look at how that's going to be done. Okay, let's solve a 3x3 system of equations with three unknowns using a matrix equation. When we solve an equation, we typically do so through some algebraic rules, using here the multiplicative inverse. When we multiply a number with its inverse, we get 1. Now, the multiplicative inverse, when multiplied by the number always resulting in 1, gives us a way of solving the equation. So on the left-hand side, if we take the inverse of m, 1 over m, and multiply it by m, okay, we'll wind up getting the x by itself, because 1 times x would give us x. Okay, so here, algebraically speaking, we multiplied by the inverse on both sides. To solve a matrix equation, you're going to do something just like that. Inverse of a matrix is going to be a little tricky. It's not as easy as just multiplying by 1 over that matrix. So we have to introduce something called the identity matrix, a matrix that sort of acts like the number 1 for matrices. Here's the idea. Take the system of equations, turn it into a matrix equation. The coefficient matrix M can be adjoined to the identity matrix, and through row operations can be changed into the inverse matrix on the right-hand side. So we're going to just quickly go through some of those row operations to see how that works. So row operations really consist of multiplying an entire row by a number and then adding it to another row to make a new row. Now, this is done systematically by trying to change the left-hand side of the augmented matrix into the identity matrix, where all the numbers along the diagonal are 1 and every other entry are 0. And so with something called Gaussian elimination, you can do this. And at the end of the day, the matrix that's left over on the right-hand side is your inverse matrix. Here, the last few entries become 1, and we identify the right-hand side to be the inverse matrix. We can now use this to solve the matrix equation. Remember, the matrix equation mx equals y can be solved for x by multiplying the right-hand side by its inverse. By doing this multiplication, we get the xyz components to be 1, 2, 3, and that is the coordinate point we saw three-dimensionally in the intersection of those three planes. Next time on Figure It Out, Part 2. How do you stretch space? Thanks for watching. Don't forget to like, subscribe, and hit that notification bell for up and coming videos.